Hello guys, so today I'll be solving today's LeetCode problem, which is create binary tree from descriptions. Okay, so this problem is not that difficult. Okay, so it's basically an implementation problem with a slight bit of tricky part is how to return the root of it. Okay, so first of all, let's focus like what the question has asked. Okay, so the question says that it has given a 2D integer array which is descriptions. Okay, and the definition of description is it has given us a parent, okay, a child, and the child position, okay, which is defined by is left. Okay, so what we need to do is, okay, we have been given a bunch of parent and child relation and which position child sits in the parent. Okay, so we have to construct a binary tree out of it. Okay, and at the end of all our building, okay, we have to return the root of it. Okay, so how to do it? Okay, so in order to do it, okay, we'll be using a couple of hash maps. Okay, so it's basically a implementation problem. Okay, so I'll just directly show you like how you guys can do it. Okay, first let's take this example. Okay, oopsie. Okay, so here as you can see, like the inputs are 20, 15 and 1. Okay, so let's say I iterate over all the descriptions. Okay, so for descriptions in descriptions. Okay, so what it has given is, okay, it has given me parent, child, and the child position. Okay, whether it is left of parent, okay, or to the towards the right of it. If is left is 1, that means like the child should be on the left side. If is left is 0, then the child should be on the right side. Okay, cool. So what we need to do is we need to somehow store the parent and the child relation. Okay, as well as the value to node. Okay, so I'll be using two hash maps. Okay, two hash maps. Okay, so what you need to do, what you need to store is, one is parent to child. Okay, so one hash map will be saying, let's call it map, basically a child to parent relationship. Okay, let's write it properly, child to its parent. Okay, this will be a int to int mapping. Okay, why int to int? Okay, so here all the values are unique. Okay, otherwise it will be difficult to build the binary tree. Okay, just imagine like node value, like basically a tree node having the same value, okay, in this kind of a description list. Okay, so with this, that will create ambiguity. So we can assume like since it has written like all the test cases will be generated such that the binary tree is valid, that means all the values you will get, that is unique. Okay, cool. So this is one map. Okay, and the second map that we'll be requiring is int to node map. Okay, so it's a value to the tree node map. Okay, so let's see how it will help us. Okay, so first thing first. Okay, so there is 20, 15 and 1. Okay, so here 20 is the parent. Okay, it's not showing up. Okay, so 20 is the parent. Okay, and 15 is the child. Okay, so what I will be storing is inside my inside my parent to child. Okay, I'll store like 15's parent, let's call it parent table. Okay, 15 parent is 20. Okay, and I'll be storing the value to node mapping also. Okay, so let's call it node mapper. Okay, so I'll be storing 15 to, let's say, the node of 15. Okay, which will be so for 15 is a child. Okay, and right now in my node mapper table, okay, there are no entries, so I'll simply push 15 with null and null, the left and right child. Okay, so it will be 15. Okay, left child will be null. Okay, and the right child will be null. okay. And similarly for 20 is the parent, okay. So 20 is the parent, which means 20. Now on the left, so we will see like on which position 15 will come. So left is given as 1, which means 15 should come on the first position, like on the left side. So I'll say this is 15th pointer, so I'll store 15 null, okay. And I have no information for the right child, so I'll be storing null, okay. So don't get confused about this, okay. So here I won't be storing the exact value of it, I'll be storing a pointer to it, okay. So I'm just showing you something like this, okay. Now let's see, there is then 27, 17 and 0, okay. Now before moving forward, one more thing we can do is, since 15 in the parent table, so child, we have a child to parent mapping, which is 15 to 20, okay. And right now for this 20th node, okay, 20 value node, we do not have a parent, so we can directly assign a 20th parent as 20 itself, okay. And later on, as you keep on like iterating over the description, you will be updating its parent, okay. Cool. So let's do for this entry also, which is 20, 17 and 0. So here 17 parent is 20, okay, and 17 is on the right side of 20. As you can see, like is left value is 0, so that means I'll be updating this node entry for 17, okay. So what I'll be storing is, first I will store this 17, okay. So here 17, and right now I do not have any information about the left and the right child of 17, so I will store them with null and null, okay. And here I'll be updating the 20th right child with the 17th node pointer, okay. So I'll just update this with 17 null and null, okay. Cool. So let's solve for this one more of this, okay. Let's call 15, 20 and 1, okay. Now for this, okay, so 20th parent is 50 now, okay. So here 50, 20 and 1, okay. So I have a 50 which is a parent of 20, okay. So here I will update 20th parent to 50, okay. And I'll check, and inside my node mapper I will check, okay, do I have 20th entry, okay. I have 20th entry. Do I need to update anything? Nope. So do I have 50th value entry? Nope, I do not have. So I'll add 50 in here, okay. And so I'll store 50 as a value and the left child of it. Now I'll see whether 20 is on the right or the left. Now here value is 1, which means 20 is the left child of it, as you can see in the tree, okay. So I'll be storing left here, okay. So here I'll be storing the 20th node pointer, okay. So I'll directly write 20 here, and right now I do not have any information about the right child, so I'll be storing a null here, okay. Let's do something like this, okay. So this I'm using like to refer to this value, okay. And yeah, and I do not have any information about the right child, so I'll be storing a null there, okay. Cool. Now let's solve for this also, 50, 80 and 0, okay. So I have a new entry, and yeah, before moving forward, 50, okay, I have a new node. So right now I do not have any parent for 50, so I'll just assign 50 as its own parent, okay. Cool. Now for this 50, 80 and 0, okay, so the updation will be something like this. So for 80 it will come as 50. Now in here 80 is the right child of my 50 value node, okay. So I'll update my 50 value node right child, so I'll just write 80, okay. And 80 is not here, so I'll just add my 80th node, okay. So this will be 80. I do not have any information about the left and the right child of 80, so I'll simply set null null, okay. Cool. Now the last part, which is 80, 19 and 1, okay. So I have 19 here, okay. 19th node value parent is 80, so 80 comes here, okay. And I already have 80th parent, okay, which is 50, so I don't need to update the parent information for 80. Cool. Now for the node updation, okay, so I have 19 here, which is the left child of my 80 value node. Okay, so I'll just update my 80 value node left child. Okay, so this will be 19, okay, and I will add 19 here to its node value. So that is 90. I do not have any information about left and right child, so I'll write null and null. Okay, cool. So after all this, okay, my tree description has been formed. Okay, cool. Now once you maintain this kind of a structure, okay, so all your nodes will be storing pointers. Okay, so in this node mapper, okay, you already have your tree data structure in place. Okay, this is already your binary tree. Okay, now in order to give out the output, okay, you need to find out which one is the root of yours. Okay, so with this, okay, we'll be using our parent table. Okay, now the beauty of parent table here is, so it will act similar to how disjoint set union works. Okay, so here we will use it as our disjoint set union. Okay, now remember, okay, this is a binary tree. Okay, which means all the nodes have the same like penultimate parent. Okay, because in a tree all of them are unified by a single root node. Okay, there are no separated nodes. Okay, it's a tree in itself, it's a complete graph. Okay, which means all the node will be pointing towards this 50 as its root node. Okay, so what I will do is, okay, I'll simply take any arbitrary node here. Okay, let's say I take this 17. Okay, let's say I take this 17. What I will do is I will take any arbitrary node, okay, or any arbitrary key, okay, from my parent table. Okay, and I will simply run the find parent method from disjoint set union. Okay, so those of you who are not aware of disjoint set union, so please have a read up on it. It's a pretty cool data structure, disjoint set union. Okay, so you can read about from here. Okay, it's basically for like it's mainly used in clustering algorithms. Okay, it's basically you have bunch of nodes and you want to group them into basically into one group, or you want to union them into one unit. Okay, so it helps in that kind of a task. Okay, now the beauty of it is, so we have a method which is find parent here. Okay, so I'll be using that idea. Okay, so I'll be using find parent logic from disjoint set union. Okay, so I'll start with 17. Okay, and I will write a while loop as while my parent of my node, okay, is not equal to the node value itself. Okay, I'll keep on updating my node to parent of node. Okay, so how it will work. Okay, so let's see. So what I'm saying is I'll start node value with any arbitrary value or any arbitrary key from my parent table. Let's say this is 17. Okay, so if I start from 17, okay, now 17th parent is not equal to 17. Okay, so 17 gets updated to parent of 17, which is 20. Okay, I got 20 here. Okay, now again in the while loop. Okay, so parent of 20, okay, which is this guy. Okay, so parent of 20, this LHS side will come out to be 50, and this node value is now 20. Okay, these are not equal. So I'll update my parent, basically this node value, to parent of 20, which is 50. Okay, so this will become 50 now. Okay, now I will look at 50. Okay, parent of 50. Okay, let's see, parent of 50 is 50. Okay, and the node value is 50. And yeah, this while loop will break, and ultimately my node will point to the root node directly. Cool, because what I'm doing is I'm starting with any arbitrary node here. Okay, you can start from any arbitrary node, okay, and just climb upwards. Okay, and as you are climbing upwards, you will always end up with the root node. So this is what I'm doing. Okay, and one more cool thing you can do here is, okay, you can perform your jumping 2x faster, okay, by doing something like this. So instead of doing node equal to parent of node, okay, you can update this value as node equal to parent of node. Okay, so here you are doing some kind of path compression. Okay, okay, so with this you will be, so see here, the worst case will be, let's say I start with any leaf node here. Okay, let's say my tree is something like this. Let's say it's a big tree. Okay, okay, so if I start with something like this, let's say I start at here. Okay, so when I'm doing node equal to parent of node, okay, this kind of updation, parent of node. Okay, so I'll be hopping something like this, like this, like this, like this, like this, and like this. Okay, so as you can see, like there are like n number of jumps I'm doing, okay, which is basically the height of the tree. Okay, but okay, if I do something like this, okay, node equal to parent of node, okay, what it will give is, so from here I'll be doing parent of node, so directly here to here jump. Okay, it's like 2-step jumps you are doing. Okay, so you are cutting your like your number of iterations, I think, by half. Okay, I guess so. Actually, yeah, it's logarithmic. Yep. So the number of jumps you will be doing is 2 to the power number of jumps is equal to height of the tree. Okay, so your number of jumps is log of your height of tree. Log base 2 height of tree. Okay, cool. So this is the logic. Okay, so you just have to maintain 2 hash maps, okay, so that you will construct your binary tree. Okay, and then you can apply this path compression logic to find out which node was your root node. Okay, because if you start at any node, okay, and you simply go up, you will always end up at the root node. So yeah, that's the idea. Cool. So I'll first code in Rust, and then I will show you the code in C and C++, like Golang and C++. So yeah, let's do for Rust. Let's make this aside. Let's go like this. Okay, cool. So first thing first, okay, I'll be needing hashmap. std. Okay, I need from collections hashmap. Okay, so I'll be creating 2 hash maps for my parent and node table. Okay, so yeah, so first thing first, so both hash map will be mutable because I'll be introducing changes. Okay, hash map I32 I need a pointer towards a node. Okay, so I'll be storing rc rf cell TreeNode this, and I'll be setting hash map new. Okay, so this will create a hash map for my node mapper, so which is like int to a tree node. Okay, cool. Then next thing will be parent. So my parent hash map will be hashmap i32. It will be hashmap i32. Oh sorry, not, yeah, it will be new. Cool. So I got my node mapper and my parent hash map. Okay, then I'll simply iterate over all the descriptions. So for let's stick to D. For D in descriptions. Okay, so I'll simply unpack it. So I'll say parent, child, and child position is left. It will be D of 0, D of 1, D of 2. Okay, cool. Now first thing first, I'll update parent. Okay, so update parent. Okay, so I'll check whether my parent hash map has an entry for p. Okay, whether my parent node has a parent itself. Okay, if it doesn't have, I'll simply insert p as its own parent, like the way we did. Okay, and I'll update the child for the child node, the parent entry. So I'll simply insert c and p. Okay, so for this child node, p is the parent node. Okay, I inserted this. Okay, and for the parent node, I simply inserted the parent node itself if the parent node doesn't have a parent. Okay, cool. Then I will update my node mapper. Okay, so first let's update for child. Okay, so what I will do is, okay, I'll say let my child node equal to node mapper. Okay, entry. Let's check whether my child node already exists in the mapper or not. Okay, let's do like this. Okay, so if let's say if it exists or not, then directly get the value. Okay, if it doesn't exist, simply insert simply create a pointer to the tree node. So I'll say rc new ref cell new. Okay, I'll create a tree node new. Okay, cool. Now I'll simply clone the value. Okay, why I'm cloning? Because rc is a pointer here. Okay, so I'm getting a reference of it. Okay, so later on I need to do this kind of updation. Okay, so I'll tell you so why I'm doing it. Okay, so similarly for the p node, let's get the node value. Okay, node, I'll collect the parent node. So for p, okay, if I have the p's entry, okay, I'll then collect that. Otherwise insert this for parent value. So rc new, again the same call, but with the parent value p. Oh, sorry, I forgot c here. Okay, and here also I will clone this value. Okay, I'm cloning this because like this inserter, it gives me a reference of it. Okay, I'm cloning this because I'll be using the child node, the actual value of it, okay, to store it in the parent node. Okay, based on the position of it, is left or is right. Okay, so simple Rust, it's specific to Rust language specific. Okay, so then I will check if as left equal to 1. Okay, now this is a ref cell. Okay, so I can borrow the mutable reference. Okay, for the parent node. So I'll say for p node, borrow the mutable reference. Okay, now once I borrow it, I can then change my left child to my c node. Okay, now the description of here is I need to store an option, so I'll directly use sum of c node. Okay, otherwise I'll update the right node. So borrow mute, okay, right sum c node. Okay, cool. So these are basically Rust syntax. Okay, but the main logic is like get the child node and the parent node from node mapper. Okay, and then simply check whether the child node should go to the left or right of the parent. Okay, and then simply assign it. Okay, this borrow, mute, insert, or clone, or entry, these are specific to Rust. Okay, but the logic is what I have described here. Okay, cool. Once you have done that, okay, so basically at the end of this for loop you are done with your tree. Okay, building the tree. Okay, because all your pointers are intact. Okay, so all your nodes have their children's and the value intact. Okay, now you need to find the root. Okay, so I'll say finding the root or finding root. Okay, so it sounds like Nemo. Let mute, let's call it root. So I'll start with any arbitrary node. Let's call description of 0 0. Okay, so from this value I will simply go upwards. Okay, so I'll say while let some let's call the reference, so parent sorry, yeah, root, yeah, oh, I cannot use this. Let's call p parent get root. Okay, so basically here what I am doing is simply this only. Okay, So I'm collecting the parent of this root node. Okay, so this arbitrary node from my starting. Okay, I'm storing the parent of it. Okay, now inside the while loop I'm checking whether p is equal to node. Okay, sorry, p is equal to root. Okay, if it is, then break the while loop, you are done. Otherwise, update your root to the p value, okay, parent of it. Okay, then do the logic again. Okay, so yeah, then finally after you are done with it, simply return node mapper dot get the root reference. So this is specific to us, but what I'm doing is I'm simply returning the root value here. Okay, because my node mapper already contains the value to the node value. Okay, the node value to the node pointer itself. So I'm simply giving the value and collecting the node pointer here. Okay, so get returns me a pointer. I'm cloning it to get the value of it. Okay, cool. So with this I should be done with it. Okay, now let's run it. Fine. Okay, descriptions. Yep, let's run it. Okay, one more mistake. Okay, insert or insert or it's or insert. Cool. Okay, not working. Okay, or insert tree.new. What is it? Undeclared ref cell. Typos. Okay, let's see. Are they same? Okay, ppp, then clone. Borrowing the mute. Should work. Fingers crossed. And voila. Okay, initial test case is passed. Now let's submit. And voila, we got acceptance. Cool. So this was the logic. Now let's look at the time complexity here. Okay, let's see. Okay, so here we go again. So let's switch to black. Okay, so time complexity. Okay, so first thing first. Okay, I am creating the hash map. So these are basically creating some pointers to the heap. Okay, so no, not much here. So big O of 1 plus big O of 1. Okay, then I'm iterating over all the descriptions. Okay, so it's a big O of number of descriptions I have. Okay, and no description is duplicate of another. Okay, so every description is unique. So I can assume the number of nodes in the tree, okay, is equal to the description length. Okay, now let's assume the number of nodes to be n. So the length of description will be n. Okay, now let's see. Okay, so I'll be iterating over n nodes in the tree. Okay, now per node I'm doing this entry and insert, which is like I hate to say it, but if I consider hash map insertion and insertion and updation as constant time, so this line is constant. Okay, but I'm not a big fan of hash map. Okay, I prefer to use BSTs. Okay, because they have the definite log n complexity. But yeah, let's assume for simplicity, let's say the hash map insertion is big O of 1. Okay, so it's a big O of 1 operation. Okay, checking whether the p value is there, otherwise inserting the node. Okay, and simply this insertion also constant. Okay, then here also, so I'm checking whether c is there in node map, which is constant operation. Okay, then I'm inserting this, which is again constant, and this cloning it. Okay, which is internally again constant. Okay, so constant still. So, and similarly for p node also, everything is constant. So these are constants. Okay, and then collecting the mutable reference and updating the left, and this is also constant. So I can say, if I am assuming insertions in my hash map are big O of 1. Okay, assuming, oh yeah, insertion. Okay, so I'll simply say create, or let's say all the CRUD operations, okay, in my hash maps are constant. Then I can simply say the length of my description will be the time complexity for this for loop. Okay, so it's a big O of n. Okay, cool. But usually this is not always the case. Okay, there can be hash collisions, but with better hashing algorithms, you can assume this is constant. So yeah, okay, let's go to the next part. Okay, so this is big O of n. Okay, then there is this finding Nemo thing, okay, which is finding root. Okay, so here I'm starting at any arbitrary node. Okay, I don't know what is this description of 0 of 0. Okay, but I know like if I start from any node in the tree and I just go up, okay, I will reach the root node. Okay, that's my belief and that's what I'm doing. Okay, cool. So from here I'm basically traversing upwards. Okay, I'm not touching all the nodes because basically I'm traversing the height of the tree. Okay, now the height of the tree in the worst case time complexity will be taking big O of so the number of n. So I know like if there are n nodes, okay, n nodes in a tree, okay, I can say the worst height of the tree will be n. Okay, let's say all the nodes are like left, something like this. Okay, so let's say with the n node binary tree, height can go n. Okay, now here I'm doing path compression. Okay, which is here. Okay, so here I'm not doing, okay, because in Rust I don't want to like bring complexities to the code. Okay, so here I'm simply iterating over all the nodes, so I can say a big O of n here. Okay, but the C++ and the Golang variant that I will show you, okay, there I'm doing path compression. Okay, so that will reduce this time complexity. But yeah, without path compression, okay, this will be big O of n. With path compression, okay, this will be big O of log of n. Okay, as I showed you here. Okay, cool. So but with that, okay, I can say my overall time complexity to be a big O of n plus n, which is n. Okay, so my overall time complexity is big O of n. Okay, now let's look at space complexity. Okay, so there are only two auxiliary spaces that I'm using, which is node mapper and parent. Okay, and at most they can contain all the node itself. Okay, so if I'm assuming there are n number of nodes, okay, so my space complexity will be a big O of n, one for node mapper and another big O of n for my parent. Okay, so this will give me big O of n. Okay, so my time complexity is big O of n. Okay, and my space complexity is big O of n, so I'm good. Okay, cool. So this was the Rust code and these are the time complexity and space complexity. Okay, now let's check out the C++ variant. Yeah, so this is the C++ variant. So here also you can see like there is node mapper, parent. Okay, and yeah, I'm again iterating over all the descriptions. Okay, I'm checking whether parent has an entry, has a parent itself. If it doesn't have, then I'm assigning the parent of my current parent as the parent node itself, and I'm assigning the child node parent as the parent. Okay, then yeah, I'm checking whether my child value has a node. If it doesn't have, then I'm updating in the node mapper. Okay, then here what I'm doing is, okay, then I'm checking whether my parent node has any TreeNode. Okay, if it doesn't have, then I'm initializing my parent node. Okay, like this, like the data structure that I showed you. Okay, so I'm storing the node value of the parent as node mapper of p as a new tree node with the parent value as the parent value, and based upon is left, if it is 1, then store the child in the left part. If it is right, then store the child in the right part, like this. Okay, now this is for when the parent node is not there. Okay, this is for initializing the parent node. Okay, but if the parent node exists, okay, simply collect the value from node mapper and update the left and the right child based upon it, whether it is left or right. Okay, so yeah, cool. So after all this, then I'm doing the find parent logic with path compression. Okay, here you can see like while parent node is not equal to node, simply update the node with parent of node. So that's all. And then from the node mapper collect the root node. So let's update to root node. Okay. Okay, so then I can directly return this. I don't need this. Okay, so let's hit submit. And voila, it got accepted. Hey, what? It was there, right? It shifted here. Bug. Okay, cool. Now I'll show you the Golang variant. It's Go but not showing. Okay, cool. In Golang variant also, so I'm creating maps. Okay, the same thing. Okay, so one into node map for node mapper and another into int map for parent mapping. Okay, simply iterate over all the description, collect the parent and the child and the position of the child where it will be inserted in the parent. Okay, check if parent exists. Check if parent exists. Okay, if it does not exist, then update the parent's parent to the parent itself. Okay, otherwise okay, then the next stage is like update the child parent to the parent value. Okay, now for node mapper, okay, check if child node has a node. Okay, if it doesn't have, create it and then store it in the node mapper. Similarly for parent node, check whether you have the parent node TreeNode in the node mapper. If it doesn't have, then initialize it and store the child node based upon the left position in the parent node. Okay, so this is this part, and then store it inside your node mapper. Okay, otherwise if it exists, okay, if it exists, then based upon your position condition, simply update the left and the right child of parent node. Cool. And yeah, then just pick up any arbitrary node, okay, and just run the path compression algorithm and you will reach at the root node. So let's update this to root. Okay, now let's submit. And voila, I'm at the last, but I got acceptance. Cool. So the time complexity is same. Okay, I don't know why I'm in the last. Okay, but I don't care, it got accepted. Okay, because I know the time complexity is linear and linear, so yeah, I'm not worried about it. So yeah, this is the logic. So this was all in the video. If you like the video, please do like, subscribe to the channel, and you can post your comment if you have any doubts. Okay, and sorry for not posting any videos like I think it's been 2 weeks. Okay, because I was actually in a shifting work. You can see my room has changed, so I'm in a new room, so that's why. Cool, but I will be I'll try to be regular in uploading videos and performing LeetCode daily on a regular basis. But yeah, I cannot guarantee. Cool, so this was all for this video. So thanks for watching, and yeah, stay healthy, and if you learn something new, please do like and subscribe to the channel. Cool, bye bye.